Good morning, guys. Today we are going to talk about geometric and experimental probability. Let's start with geometric first. Okay, so it's a form of theoretical probability determined by a ratio of lengths, areas, or volumes. So remember, a ratio means a fraction. So in our first example here, it says 3 semicircles with diameters 2, 4, and 6 are shown in the figure. If a point inside the figure is chosen at random, what is the probability that the point is inside the shaded area? Okay, so if I choose a point, what's the probability I'm going to get into the shaded area? Okay, so we're going to find the ratio of the area of the shaded area, and it's going to be over the area of the entire semicircle. Okay. So the area of a circle is pi r squared. So the area of a semicircle, which is half of a circle, is half times pi r squared. So our steps are as follows. First, we have to find the total area of the largest semicircle. Okay, so if I'm looking at the largest one, I see a diameter of 6. So I know the radius is half of the diameter. So it's going to be 3. So the total area of this semicircle is 4.5 pi. Okay. Now, the sum of the areas of the unshaded semicircle. So I need this one plus this one. Okay. So the first one is 4 centimeters. That's a diameter. So I take half of that, which is 2. So it's half pi times 2 squared, which is 4. And then the other one is 2 centimeters, so half of 2 is 1. So I take 1/2 pi times 1 squared. So my first one is 2 pi. My second one is 0.5 pi. And if I add them together, I get 2.5 pi. Okay, so now I have the area of the big semicircle. And now I have the area of both of the little ones combined. All I'm going to do is subtract to find the shaded area. So I take my big semicircle area, 4.5 pi, and I subtract the 2 that I just added together, which was the 2.5 pi, and I get 2 pi. So the ratio of the shaded region to the total area is 2 pi over 4.5 pi. So we're taking the shaded area over the entire largest semicircle. So then the pi's will cancel, and I get 2 over 4.5. And I don't like decimals, so I'm just going to multiply both by 2, and I get 4 over 9. Okay. Next, we are going to move on to experimental probability. Okay, so this is the ratio of the number of times that the event occurs, which we call the frequency, to the number of trials. So with experimental probability, you are actually experimenting. You are actually doing it, and you are recording your results, okay? So the number of times that happens over the number of times that you tried. Our first example is, let's move this up. The bar graph shows the results of 100 tosses of an oddly shaped number cube. Find each experimental probability. Okay, so here's my little grid I'm looking at. Here's my oddly shaped number cube. The frequency of how many times it happens and the number rolled. Okay, so I did 100 rolls, and this is how many times. 1 happened 17 times, 2 happened 21, 3 happened 16, 4 happened 11 times, 5 happened 22 times, and 6 happened 13 times. So my first question is, okay, well, what's the probability of rolling a 3? Well, I come over here to say, okay, well, how many times did 3 happen? It happened 16 times. How many total times did I try? Well, I did 100 trials, so it's 16 over 100, which I can reduce to 4 over 25. Okay, The next one is rolling a perfect square. So if I look at 1, 2, 3, 4, 5, 6, these are all the faces on a number cube. Which ones are perfect squares? 1 and 4 are my perfect squares. Okay? So 1 happened 17 times and 4 happened 11. So I'm going to add those together over the number of trials, 100. I get 28 over 100, and I can reduce that to 7 over 25. Okay, the last example, rolling a number other than 5. Okay, so other than 5 means I don't want 5. So I'm going to use the complement. So the probability of rolling a 5 is 22 over 100. I went to 5 and I found it happened 22 times. So this is the probability of rolling a 5. But I don't want that. I want rolling a number other than 5. So I'm going to do 1 minus 22 over 100. And I'm just going to change this 1 to 100 over 100, which is still 1, minus 22 over 100, and I get 78 over 100, which I can reduce, split it in half, 39 over 50. I want to do a couple more examples with you. All right, let's look at this one. Just hide this. All right, a clerk has 4 different letters that need to go in 4 different envelopes. What is the probability that all 4 letters are placed in the correct envelopes? Okay, using the word correct, I know that order matters, so I'm going to use a permutation. So I have 4, I have to choose 4. So my formula is 4 factorial over 4 minus 4 factorial, which gives me a 4 factorial over a 0 factorial. 0 factorial is always 1. So now I have 4 factorial, which is 4 times 3, which is 12, times 2, which is 24. Okay? So whenever you have these problems, I want you to say, does order matter? Are there any key words in this word problem that tells me order will matter? Okay, my next example. There are 12 balloons in a bag, 3 each of blue, green, red, and yellow. 3 balloons are chosen at random. Find the probability that all 3 of the balloons are green. Okay, so I have 12 balloons in a bag. There are 3 of each color, so I know there's 3 green. So the probability of me pulling a green the first time is 3 out of 12. Now, they did not tell me that I put that green balloon back. Okay, so imagine taking it out of the bag, putting it over to the side. Now my second pull, for me to pull another green, well now I only have 2 greens left in the bag, and there's 11 total balloons in the bag. Remember, that other green I kept out. So that's 2 over 11. Now I have 2 green balloons to the side, and I have 10 left in the bag, and one of them is green. So when we are looking at probability of multiple things happening at once, we are going to multiply. So 3 times 2 times 1 is 6. 12 times 11 times 10 is 1,320. And I can divide that by 6, and I get 1 over 220. All right, the last example, we're going to use this diagram for exercises 10 and 11. So 10 says that a point chosen at random is in the shaded area. So first you have to figure out, okay, well, I've got 3 different circles. I have a big circle, I have a medium circle, and I have a little circle. So if I look at the little circle, I need the area of that. That's going to be pi r squared. So my diameter is 4, r is going to be 2, so it's 2 squared, so it's 4 pi. My middle circle, again, pi r squared. What is my diameter? They only give me this little piece right here, which is 2. Well, remember, the inner circle is 4, So if I were to draw a line all the way through the shaded area, I would have 2 here, 4, and another 2, which makes a diameter of 8. So half of 8 is 4 squared, and I get 16 pi. And then the large one, again, imagine drawing a line all the way across. So this is 2, the shaded area is 2, the center is 4, the shaded area is 2, over here is 2 again, that's 12. So half of 12 is 6, and 6 squared is 36 pi. Okay? So a point chosen at random is in the shaded area. I'm going to take my shaded area circle, okay, including the center, which is 16 pi, and I'm going to subtract the center, which is 4 pi, and I get 12 pi, okay? But I want that as a ratio, so it's going to be 12 pi over the entire area, which is 36. So my pi's cancel, 12 over 36 reduces to 1 over 3. 11. That a point chosen at random is in the smallest circle. So again, we want the ratio. I know the area of this small circle is 4 pi. I know the entire area is 36 pi, so it's going to be 4 pi over 36 pi. And I can reduce that. The pi's cancel. I get 1 over 9. Just a few more examples I want to review. All right. We are going to use this table. So we have a spinner experiment, okay? We have red, green, and blue on the spinner. Find the experimental probability of spinning a red, okay? So first you have to figure out, well, how many spins in total did I take? So you're going to add all of your spins together. 5 plus 8 plus 7, I did 20 spins. So the experimental probability of spinning red happened 5 times, so it's 5 over 20, and I can reduce that to 1 over 4. All right, for this one, find the experimental probability of spinning red or blue. So I really want you to pay attention to this word, or, okay? When you see or, we are going to add the ratios together. When we see and, we're going to multiply. So this says, what's the experimental probability of spinning a red or a blue? Okay, so red is 5 over 20. Blue is 7 over 20. I'm going to add them together to get 12 over 20, which reduces to 3 over 5. So this rule, write it, highlight it, make sure you remember with probability. When you see the or word, you are going to add the ratios. When you see and, we are going to multiply. All right, good luck, guys.